Experiment S2. Sound resonance in air column. Objectives. 1. Investigate resonance in an air column with one open end and one closed end. 2. Measure the speed of sound in air and determine the frequencies of unknown oscillators. Theory. Standing waves are formed when two identical waves travel in opposite directions in the same medium. This results in combining these waves according to the principle of superposition. The unique properties of standing waves include fixed points called nodes and antinodes. Nodes are positions where the waves cancel each other completely, resulting in no displacement. Antinodes are positions where the waves combine constructively, producing maximum displacement. Standing waves of longitudinal waves. When sound waves, which are longitudinal in nature, travel through an air pipe and reach the end of the pipe, they are either reflected or transmitted. The reflected waves will combine with the waves originating from the source. When the pipe length matches the wavelength of the sound wave, standing waves can form. Conditions for the formation of standing waves in an air column with one open end and one closed end. The open end corresponds to an antinode, where maximum displacement occurs, while the closed end corresponds to a node without displacement. The distance between two adjacent nodes, or antinodes, represents 1/2 of the wavelength. Natural frequency of an air column of length L. For an air column with one end open and the other closed, the open end corresponds to an antinode, and the closed end corresponds to a node. In the fundamental mode, the air column has one node and one antinode, resulting in the maximum wavelength and the lowest frequency. From the figure, the length of the tube L is equal to 1/4 of the wavelength in the fundamental mode. Thus, the fundamental wavelength lambda is 4 times the length of the pipe, or lambda equals 4L. By substituting the values into the equation V equals F lambda, we get the fundamental mode frequency. F1 equals V divided by 4L, where V is the speed of sound in air. The natural frequency in the next mode is called the first overtone. The frequency in this mode is 3 times the fundamental frequency, so it is also called the third harmonic. In this mode, there are 2 nodes. From the figure, the pipe length L equals 3/4 lambda. Therefore, lambda is equal to 4/3 L. Substituting these values into the equation V equals F lambda, we find that the third harmonic frequency is F3 equals 3V divided by 4L, equals 3 times of F1. The natural frequency in the next mode is called the second overtone. This mode has a frequency 5 times the fundamental frequency, so it is also called the fifth harmonic. In this mode, there are 3 nodes. From the figure, the pipe length L is equal to 5/4 lambda, so lambda is equal to 4/5 L. Substituting these values into the equation V equals F lambda, we find that the second overtone frequency is F5 equals 5V divided by 4L, equals 5 times of F1. As an example, consider the natural frequencies of a pipe with one open end and one closed end in the first 3 modes. We conclude that the frequencies contain only odd harmonics. Therefore, the natural frequency of a pipe with one open end and one closed end is given by Fn equals Nf1, where F1 is the fundamental frequency, equal to V by 4L. The wavelength in the nth mode, lambda n, is equal to lambda n equals 4L by n. Here, V is the speed of sound in air, L is the length of the pipe, and n takes on odd values, 1, 3, 5. Resonance. Resonance occurs when a system is stimulated by a frequency that matches its natural frequency, causing the system to vibrate intensely. For example, Consider the resonance of an air column with one open end and one closed end, with length L. Fn equals n multiplied by V by 4L equals n F1, where n equals 1, 3, 5, etc. Here, F1 equals V divided by 4L is the fundamental frequency of the system. If we have an air pipe with one open end and one closed end, its natural frequency will change with its length. Today's experiment will stimulate an air column to vibrate by emitting a sound at a fixed frequency. To create the phenomenon of sound resonance in the air column, we will need to adjust its natural frequency to match the sound frequency from the speaker. The first air column that causes a resonance phenomenon and produces a louder sound than normal will be the pipe with the shortest length, L1. The speaker's sound frequency matches this pipe's fundamental mode frequency. Thus, the sound frequency from the speaker is F1, which is equal to V by 4L1. Note that in the first figure, it is obvious that L1 equals lambda by 4. We extended the pipe length to 3 times that of the initial pipe, L1. This relationship is expressed as L2 equals 3L1. As a result, we observed that the third harmonic of this pipe corresponds to 3V/4L2, or equivalently, V/4L1. Therefore, the third harmonic frequency of this pipe aligns with the sound frequency produced by the speaker we are driving, enhancing the sound's loudness through resonance. Similarly, if we adjust the air pipe length to 5 times that of the first pipe, denoted as L3 equals 5L1. Observing the fifth harmonic of this extended pipe, we find its natural frequency to be 5V/4L3, or equivalently, V/4L1. This fifth harmonic frequency of the third pipe coincides with the sound frequency emitted by the speaker we are driving, leading to an increase in sound intensity due to resonance. Note that in the first figure, it is obvious that L3 equals 5/4 lambda. Therefore, if we know the lengths of the first 3 resonant pipes, we can determine the wavelength of sound as follows. L2 minus L1 equals 1/2 lambda, hence the wavelength lambda equals 2, L2 minus L1. L3 minus L1 equals lambda, thus the wavelength lambda equals L3 minus L1. If we know the sound frequency F that induces resonance, we can determine the speed of sound in air as follows, V equals F lambda, where lambda is the average wavelength of sound obtained from the experiment. Alternatively, if we know the speed of sound in air, we can find the frequency F of the stimulating sound using the relationship F equals V over lambda.